Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 9 of these recorded sessions. So today we'll be going over for most of y'all Chapter 21 and in general aldehydes and ketones with nucleophilic addition. So last chapter we talked a little bit about aldehydes and ketones in regards to carboxylic acids, things like that. So now we're breaking off and now we're talking about different functional groups, right? And again, with different functional groups, kind of like stacking our cards, right, or stacking our resources in terms of like the basics, things like that. So you'll see a lot of um, same concepts that we've learned before, but applied to this new functional group that we're learning about, right? So, again, as always, we'll be doing review first, 20 questions. Do whatever you will with that, whatever your strategy is. Hopefully by now you're up to date with everything. You're used to everything. You kind of have the hang of it, right? So, do whatever you need to. Do whatever is most beneficial for your, studying things like that. And with that being said, let's get started with the review. So, again, pause video, um, take notes, screenshot, do whatever. And, if you want to go along with the video and answer these questions with me, feel free. So, number one, you guys should have gone A, right? Which is the most reactive carbonyl compound. We know that um, aldehydes are more reactive than ketones, right? Because aldehydes are, in general, not as hindered, and which is one, right? Between 1 and 3, the most unhindered is 1. And it's also not because of just the hindrance and stuff like that. It's also because of the donating groups, right? So 3 obviously is a bigger donating electron donating group than the ethyl group in 1, right? So, and I guess you could do electron withdrawing group, right? Okay, so 2, again, like I said with the basics, right? New functional group, new basics for that functional group. So new naming. Um, we'll see a little bit of again colligative properties, things like that. But we all know this. We all know that you know carbonyl aldehydes ketones, the double bond, the pi bond, do what they do, right? So what is the structure of 3-methyl cyclohexanone? Hexanone, ketone, right? So for this one, you guys should have gone B. And again, kind of same with the common names for the carboxylic acids. This time we care about the ketones and the aldehydes, right? 3, what is the structure of benzophenone? This one you guys should have gone B as well. And this is one of those, again, um, it's not a common name this time, but you have ben, benzophenone, the phenone again, you know, phenyl is just the substituent name of the benzene. So you have a benzene, and then you have a phenyl group, which is B, right? And just to clear that up here, so pretty much since they're symmetrical, you can just pretty much pick whichever one's your parent, right? So in this case, this is your parent, right? And then this is the substituent, phenone, right? And this is the benzo part. So same tricks, right? Same tricks for naming, just a different ending, pretty much. So 4, we should have found we'll have the highest wave number. This one, you guys should have gotten A. And this one is the IR spectrum. We know um, cyclics, because we know aromatics for sure in the 1600s, right? 16, 1700s, but these are not aromatics. These are just cycloalkanes, right? Or cyclo, I guess, if you want to call it cycloketones, right? So the trick for this one is that the more strained equals um, the higher wave number. And remember, the more you, the more the bond angle deviates from 109.5, the more strain, right? So don't forget that. But you know, just the basics again. This is going back to hybridization. This is going back to what's called IR, right? Spec. So okay, next page. What compound is consistent, or I guess pause the video. Let you pause the video, and again, take your time, gather your notes. You know. Okay. So five. What compound is consistent with following H&MR? So again, we've seen this type of questions before when we were going over H&MR, spectroscopy, things like that. So this shouldn't be a surprise. And again, right, new functional group, we're gonna go back to all the basics to kind of review. So it's always good to review, and getting repetitive is always good because then the more you see it, the more you do it, the more you remember, right? And this will only have help for the final. And that's kind of the thing that's good about these is because you always keep refreshing, right? So and basically as the topics, as the sessions, as the chapters go on, you kind of cover less and less because you know for sure you're going to cover naming, hybridization, spectroscopy. So that's good. Okay, so this one you guys should have gotten C, and why C? So we have acetone, propanol, cyclobutanone. Oh, this should be four. Let me erase that. Cyclobutanone. So again, I like to draw these out because seeing them visually is better for me. And then we have two butanone, right? So which one of these follow this HNMR? Um, again, this HNMR is has two environments, right? This only has one environment, so that's a no, right? This has one, two, three environments, so that's a no. This one has one, two environments. This one has one, two, three. So we didn't even really need to do anything with that. We just needed to figure out the environments, and we're given it was cyclobutanol, right? And if you want to take a step further, this one, this first environment has how many hydrogens? Two, four, four, right? And this one has what? Two. So what's the ratio? 4 to 2, and this equals what? 2 to 1, which is the ratio we have up here, right? And with the ratios, don't forget you you always reduce them. You always find a common denominator type thing, right? So 2 1 is exactly what we have. Two hydrogens for the first, right? The first environment, and then one hydrogen for the second environment. So that's that. And you can even do the splitting pattern as well, because for the question, they had the splitting patterns. So, okay. Six, what is the first step in nucleophilic addition under acidic? conditions. So you guys should have gone here. D, protonation of carbonyls. Again, this is one of those basic acidic conditions. Obviously, we're going to protonate because it's acidic, right? And also for just in general, the first step is what? Right? Protection. Second, nucleophilic attack. Third, deprotonation. Right? Protonation. Okay. There. Nucleophilic attack, deprotonation. Right? Okay. So 7, what is the major product of the sequence of reactions? So what do you guys think is going to happen for this one? So this one's a good one because you kind of need to know the intermediate, or I guess understand the intermediate to even know the product. So for 7, you guys should have gotten C, but hopefully you guys found out the intermediate as well, right? So this is one of those questions that you try to figure out as much as possible, so you can practice as much as possible. So what's our intermediate here? You guys should have gotten something like this, right? And that's so CH3 2 CH2 CH2, right? So I think I'm missing one carbon here actually. So I'm just gonna, okay, that's bent, right? I made it worse, but this is 1, 2, 3, 4. Okay, this should be your intermediate, and then you get oxidized, right? And you just end up with C. But yeah, and you see how this isn't really what's it called, a specific reaction, right? We know this is an organic gradient reagent, which is from last chapter. We know what it does. It just attaches that R group, and then we know CrO3 is oxidizer, so it just makes a double bond, right? So there's no specific reaction here. It's just using what we already know. Okay, so let's go with 8. So 8 is like a new one. Um, this one is pretty involved, I should say. So we know for sure this is talking about Wittig reaction, right? But this specific question is not a Wittig reaction. Um, this one is more like a really Wittig formation. So it's making that reagent so we can use it later, right? Does that make sense? So pretty much this is, and also Eli formation, right? Eli formation. So what do we know about Euclidic and Eli formation? You need what? You need A, because what's the steps for the formation of the Eulide or the Wittig? So first you'll have an SN2 reaction with RX to form salt, right? So that's what we have. This is what the reactants right now. We're in the salt form, right? But now the second step is the one we're looking for, is that the protonation of salt with strong base. So this strong base, and you guessed it, um, these are going to be the common ones, butylium, right? Pretty much anything with lithium, you're good. So that's why we chose A, because this is literally how you make it. Um, and again, in number 8, we're starting off with the salt already, so we're here, right? And then that's asking us for the strong base, basically. So that's it. Okay, let's see. Let's go to the next page. Okay, so again, pause, stop, take notes, answer them, see what you guys got. Okay, you guys are back. 9, you guys should have gone D. What is the product of the following reaction? So D, and I think we saw this last video as well, where we're making what? Enamine from secondary amines, right? And then imines, which is what choice? Which is choice A, right? From um, primary amines. So again, taking that step further. So what we would need to do to make an imine, right? And we know how to do that. So that type thing. Okay. 10. What needs to be done to make the following reaction proceed? So this one is an interesting one because it's one of those things that's just random, I guess. But in this case, we know this is pretty much, I want to call this an acetal formation because it's part of that step process. This one is just kind of, instead of going straight to acetal, it's getting an intermediate with that protecting group, right? So it's kind of like an intermediate before the acetal. So I have it in quotations. But this one, you guys should have gone D, because for sure we need an acid catalyst. Um, but heating it up also is necessary for that protecting group, right? Because for sure acid catalyst, because acid catalyst um, drive the acetal formation, right? But in addition to acid catalyst, with heat, it protects it as well. So, but with diols, right? So, okay. 11. What sequence of reactions is required for the following transformation? So what's going on here? So this one is also a good one, right? Because obviously we got rid of that leaving group and added our double bond and R groups, additional R groups. So pretty much just an R group, right? So this one, C, right? And between B and C, why did we choose C? Again, we chose C for that base, right? So basically, C is the Wittig formation itself, if that makes sense, right? So, and D is pretty much the um, opposite of what you're trying to do. And then A, I don't know what that's trying to do, um, but it's not gonna make not gonna make that, right? So okay, but yeah. So again, this Wittig reaction is for sure gonna give us alkyl groups that has a double bond, right? So that's a given. Let's see. Actually, let me write that. With double bond, right? Okay. So let's go on to the next page. So we're going pretty fast because there's not since well, I guess it depends on your professor, but um, if they want you to learn every single step, every single mechanism, but literally as long as you get to the product, you're good. Because yeah, you shouldn't get any more detailed questions than that. Okay, so again, you guys know what to do. Okay, so you guys are back. 12. Actually, this is one of our choices, right? 12, you guys should have gone A, right? So it makes what? Ethers, right? So ether formation. And 2, kind of a little bit tricky, right? Because we said earlier that we needed heat and acid to protect, but that one we didn't need R groups, right? Or we didn't need um, alcohol with an R group. So don't get that confused or don't get that mixed up. And let's see, 3 and 4 are just plain wrong, right? Because how did the double bond get there? Why is it inside the ring now, right? So, okay. 13, what is the following reaction? MEOH. So, what do you guys get? This one, 13, you guys should have gone pretty much same answer, which is A, right? So, not too crazy. It's pretty much exactly the same. This one, let's see. Yeah, nothing. Even the choices are the same from the number 12. So I guess that's good, right? Okay, so nothing new with that one. 14, you guys should have gone, what is the missing reagent in the reaction below? So this one, what did it make? An amide, right? So in order to make an amide from a carbonyl, what do we need? An amine, right? So this one you guys should have gone B. So let's draw this one. Again, if I were you guys, or I guess I would always draw these out. So, to kind of a better visual. So we chose B, diethylamine. So something like this, right? Right, diethylamine, and then mild acid. Okay, and pretty much we added that diethylamine, right, to that O group, and this is exactly what the product was, right? So nothing too crazy. Um, yeah. Okay. Let's go on to 15. Okay. So again, you guys know the drill. Okay. 15. You guys should have gone B, and this one's a good one too, because this one we need to draw, because this is a formation of cyclic hemiacetal. So did I draw that right? Okay. And H3O, which is pretty much H3O, which is the acid, right? We said earlier that we need acid to make acetals. Same thing with hemiacetals, right? So, how do we get from our reactant to B? So, this is what you kind of have to look for. This carbon closes to this oxygen, right? So let me draw it for you guys. So and then HO. So this is where the new bond is, right? So you can kind of see how it closed up, right? So yeah, nothing too crazy. Pretty much just count the carbons. Don't lose track of them. Um, and also kind of like see where those what's it called? Where those atoms fall. And actually, sorry, I chose the wrong oxygen and the carbon. So the blue, don't pay attention to the blue. So let me erase this. Hopefully you guys caught me. Okay, so let me redraw this. Oh, was it the... Okay, so let's try this again. This time, let's do it with the green. Okay, so it's this, right? So pretty much the same thing, but right. Okay. Oh, I drew that wrong. Okay. Okay. So sorry about that. So the green, follow the green. Um, and that's it just closes up, right? And of course the carbonyl turns into OH, the HO turns into just this internal oxygen, I guess. Um, and yeah, and it's closes, and we've seen this before. We've seen intermolecular reactions before, so um should nothing should be shocking, right? And just again, don't follow blue. Count your carbons. We have here 1, 2, 3, 4, 5, and then 6 is with your O, right? So, okay, 16. Which of the following product is formed by the Wittig reaction with pH 3P CH3? So this one, we kind of saw this, but in a different molecule. So 16, you guys should have gone D, 1 and 2, because so this is where it kind of gets more conceptual. Wittig reaction, you know, you see how 1 is obviously trans, 2 is cis, so it doesn't have a preference, right? So racemic. So just keep that in mind. I mean, unless there's not a lot of reactions that we've seen, even last chapter or some of the chapters before, that they're very specific to like stereochemistry and things like that. So, we shouldn't be too concerned with that with this chapter as well. So, 17, what is the product of the following reaction? So this one, what do you think is going to happen? Stay closed, open up. So for 17, you guys should have gone B, So they just added the R group again, right? And this one, what is the reaction going on here? So this is gonna be pretty much a hemiacetal going to a full acetal, right? So we had the hemiacetal going to a full acetal. And acetal has two OR groups, right? So we have OCH3 here. Hemiacetal only has one OR group, which is this one, right? So this one over here is counted as an OR group. So don't forget that. That's probably one of those things that's very easy to forget. One of those things because you wouldn't expect to call this an OR group, right? Kind of just like there, but it is an OR group because it's surrounded by obviously R groups right there, right? So okay, let's go to the last. Yeah, last page. You know, take your time. Okay. 18. Identify how you could synthesize an enamine, and again, we did it earlier. You guys should have gotten A. Enamines from secondary amines. Not a big deal. 19. Cyclic acetals are used as protecting groups, which is what we saw. For ketones and aldehydes because they're inert to all the following reagents except acids, right? So we know acids, if you didn't know already, acids can reverse all reactions as well as go through reactions. Um, so aldehydes, ketones go through acetal with acid. So we can go back and forth using acid. So that's why um, protecting groups are necessary. Okay, 20. What is the product of this one? So this one's a good one too, because what do you guys get? You guys should have gone B, right? So why B? So say it to me, I'm listening. So why didn't both OH um, get affected? So same as the, I guess, last page question, number 17, right? Um, this is going from hemi to acetal. So, let's draw the same thing. And it's almost the exact same structure, but with this added alcohol group, right? So why did we only use this one? So the important thing here is that only the hemiacetal alcohol gets affected, right? Hemiacetal alcohol gets affected. So don't forget that. There may be OHs over here as well, but we only care about the hemiacetal, which is the one adjacent to the OR, right? So don't forget that. That's one of those things that you cannot confuse because it's really easy to forget. You could have easily chosen one, right? Because that technically is still an acetal, right? For sure not four because we're not cleaving anything, right? So yeah, how was that review? Pretty decent. I thought it went by fast. I feel like I've been saying that a lot in the past few chapters, but that's what it feels like. And I guess that's good. If I feel it's fast, hopefully that means it's fast for you guys too, so it's not too unbearable, right? But let's get into our summary. So obviously, let's start with aldehydes and ketones. So again, we know the sp2, they're carbonyls, right? They're electrophilic, and I feel like I wrote the same thing for carboxylic acids, right? And reactivity wise, COO is more reactive than RCO, then R2CO. So pretty much aldehyde to ketone, right? To ketone. Um, Now with I'm kind of jumping the gun here, but since we're talking about both of them, so both the reactions they can have oxidation, oxidative, I guess I should say, cleavage of alkenes, right? Using zinc, things like that to make carboxylic or carbonyls, right? Which is pretty much carboxylic acid because we know we're going to use O3, ozonolysis, right? So we have O3 plus um, H2O or CH3, and I think this is a new one, CH3, to make carboxylic acids, right? And carbonyls. Well, with carboxylic acids, we'll get our aldehydes or ketones. So, okay, and then the next thing, they have two different, and this is where the main part of it is, but we'll kind of save it for later. This is they have both sorry about that. Both aldehydes and ketones have the same types of reactions they can undergo. One of them being nucleophilic addition, which we saw in a review, right? And then the other one is the alpha carbon attack. So two ways to kind of approach aldehyde and ketone reactions, right? So keep that in mind, and this is the reaction types, right? Okay, so now let's get into more specific. Let's go to aldehydes first. Okay, so we know just for naming, it's gonna be oh sorry, al. I don't know. I just kind of wrote this subconsciously. Okay, al, not own, right? And then it has common names. I don't think we did a lot of common names actually with naming in the review, but al, and then with double bond, ene now, right? Because it's an alkene, but this time with an aldehyde. Okay, and what if it's a ring? Ring plus carbaldehyde. So let's go to the common names. Oops. Common names, right? we have just a couple, and this also kind of relates to the carboxylic acids because they have the same kind of root words. So we have here formaldehyde, right? And then we have here acetaldehyde, right? And this kind of again carboxylic acid because formic acid, um, acetic acid, right? They have the same amount of carbons. And then of course we have the benzaldehyde. Benzaldehyde, right? So I'm gonna go to a new page because this second part is a good block of like important stuff. And again, you know, compare notes. Don't just well feel free to because obviously I'm giving it to you, but personally I like to keep mine in page and then write everything in it, right? So everything about aldehydes, one half the page, everything about ketones, the half of the page, right? And then organize them however you will. Take additional notes, right? And colorful pens, things like that. So, okay. So now this is the preparation of aldehydes. So first we have oxidation of primary alcohol to see, to carboxylic acid, or I guess to aldehyde, right? And this is using PCC. So we've seen PCC a lot. So nothing too crazy there. And you'll be seeing PCC a lot just with carbonyls and double bonds in general, right? Second, reduction of esters using, you guessed it, Debol H and acid chlorides using, this one's a long one. It never fits whenever I write it. Okay, but let's try. LiAl H O C parentheses CH3 3 3, right? With H2O. Okay, it fits. So reduction of esters and acid chlorides to aldehydes, obviously. And three, and okay, good thing we have room. Hydroboration. So we haven't seen hydroboration in a while, right? Boration of alkynes. But we know hydroboration is anti-Markovnikov, things like that. But why is this here? Why is it an aldehyde? Well, let me draw it so kind of refresh. Since this is way back in OCHEM 1, right? So let's refresh. And we know it's BH3, H2O2, H2O, or OH minus, I should say. And then basically it's going to make RCH2CO. So it just got um, reduced, right? Or I guess oxidized in a way. So yeah, we'll reduce because of the CH2. So yeah, and then the double bond at the end. Pretty much the R group disappears, right? So we have an R group somewhere. So this is the preparation of aldehydes, right? Nothing too crazy. Pretty much 1 and 2 we know. 3, if you remember OCHEM 1, then we know, right? Okay, now let's jump to ketones. So with ketones, we're ending with "-one". So there's the "-one". And also with double bond, "-enone", right? "-enone". Okay. So again with the common names. So again, same concept. We have an acetone, and we saw these more than we did aldehyde stuff, but acetophenone, right, and benzophenone. So pretty much this is naming both the groups and then the ketone, right? And then we also have groups as substituents, so acyl groups. And acyl groups again, reminding you of Friedel-Crafts acylation, right? So this is pretty much like that. So we have C, which is a 4-mel group, 4-mel. I feel like I'm missing the M. Okay, 4-mel. And this is where they're attached. And this one's the acetyl, right? So same thing. We had acetyl too, the last one. And then benzoyl, I guess. See? Substituents always YL, right? So acyl groups. So now, let's go to the new page for the preparations. So, first we have oxidation of secondary OH, so different from aldehydes, right? Using Cr chromium reagents, right? So that's no surprise. Chromium is the best oxidizer, right? Two, um, acid chloride with organic cuprate, right? Li. Um, three, Friedel-Crafts. Speaking of Friedel-Crafts, acylation. So, and that one's just AlCl2, right? Right. And then also hydroboration or hydration, I should say. I can't even read my own notes. Okay, that's life. So hydration of alkynes. So same concept as the hydroboration, but this time we're not using boron, right? So hydration, of course, just a lot of hydrogen, H2O, 4, HGSO4, CH3, right? So that's it. Preparation, and we saw this for sure. 1, 2, 3, we know, right? Um, well, I guess 4 too, but this is really not what we're focused on here, but it's good to know just in case, right? It's good to have it in your little note card or notes, study notes, right? So now let's move on to the good stuff, which is the reactions of nucleophilic addition, which is what the chapter is about. Addition, right? So nucleophilic addition, first step, nucleophilic attack, right? That's what we got asked that on the study review. Second step, protonation. So this one, it has different levels. So hopefully it doesn't get confusing. But we have an acid catalyzed, right? Which is kind of a backwards thing, and we've seen this before as well with the most recent is the last chapter, but it was like a tiny bit it's not a main topic, I guess. But if it was an acid catalyzed, first step is protonation. Second step is the attack, and then third step is deprotonation, which makes sense because protonation, this is an acid, right? Um, so acids are protonated. So and now we have good nucleophiles, and we know what good nucleophiles are, right? Pretty much weaker bases. Oh, weaker bases. So I totally just misspelled that. But weaker bases are better nucleophiles. And just another tidbit, um, equilibrium favors it, right? Favored. Equilibrium favors weaker bases. So just for your information, I guess, because we're not really looking for good nucleophiles or bad nucleophiles, because by now we know what they are. But just know that equilibrium favors weaker bases, and I think we talked about that earlier as well. So that's that for that, right? So kind of this is um, an intro to the reactions themselves, and we have a couple of reactions. We have 7, right? And some of these are obvious ones. So let's start off with um, our decoy, right? So there's 7, like I said. So let me try and so this will be the middle. 1, 2, 3, 4, 5, 6, 7. So this is literally what my notes look like. So okay. So first things first, CH4 or LiAlH4 with H2O, and we have RMGX or RLI with H2O. I thought I had enough room, but okay. So first things first, this is gonna make what? Just an OH. So I'm just gonna twist it so it's not too crowded. And same thing over here, OH with an R group this time. Okay, what's next? We have CN with HCl. So OH with a CN group, right? So some of these are kind of very obvious, but and this is the Wittig, right? But let me just write it down. pH 3, P plus, Cr2 minus, and you end up with this Cr2 with a double bond. So pretty much literally switching that oxygen to the Cr, right? Now we have, here we go, we have room. RnH2 with mild acid. Oh, I just realized I've been putting circles. So these aren't aromatics, I'm sorry. So just erase those. I don't know why. Okay. R2NH with mild acid. So you already know what's going on over here, right? R2N and then a double bond over here, right? So I'm gonna erase the circles later. So, and then last but not least is ROH and H plus, which is what we saw earlier. So these don't really have names, so it's kind of hard to remember them, or kind of hard to like pinpoint them because some names. Let me erase these what I thought. Some names you can kind of give away the reaction, but these don't have names, so this kind of makes it a tad annoying to kind of memorize, kind of study and stuff. But some of them have names, like the Wittig one has name, and I guess this one's just reduction. And I guess the organometals have names, right? Okay. Okay. So that's that, and nothing too crazy. Pretty much, it is what it is, right? It's very straightforward, and yeah, all you have to do is remember these. Your new set of reactions, right, for your little chart or for your little study guides, right? So hopefully you guys have been stacking those reaction tables, right? And I don't know if they have an exact chart in your book or not, but I know this is what I did this is what I do to organize my reactions. So, okay, enough about that. So now let's go with the Wittig reaction. So I'm going to signal this out because it's an important reaction, but pretty much is what we saw. But let me draw it. Since we're spotlighting it, let's draw it out. Okay. So then we have pH 3, P plus, R minus, or I guess not R minus, but right, and then plus pH 3, P O. So that's where the O went, right? So this is our Wittig alkene and the oxide. So this, how do we prepare this, right? SN2 with RX to form salt, and 2 deprotonation with strong base, aka pretty much the lithium, right? So that's how we get here. And now we can use this
to do the reactions. And pretty much it's adding alkenes, right? Organometals added alkanes, alkyl groups, right? This time we're adding alkenes. So that's good. And that's why Wittig reaction is used other than organometals is because of that. So let's go from there. And I know we kind of talked about this in the review, but for those of you who guys skipped it to get to the summaries, um, let's not leave anything out, right? And this is so important. So we saw this in our little web earlier, the nucleophilic additions, right? So we'll just get their little on spotlight. Amine with H2O, secondary amine with H2O. Okay, NR. And we get NR. And you notice where the double bond kind of goes to. Um, so pay attention to that. Amine and amine. Right. So pay attention to that. So, and also this one, if the intermediate is obviously iminium ion, because it's an imine, iminium ion intermediate, and this one has H. This one same thing, but has no H, right? Because of this bond over here. Okay, so that's that. And now the next little reaction is the hydration. And we didn't see this at all, but you know, hydration of aldehydes ketones. But I think it's worth noting because it's pretty much just hydration. Well, actually, we did see it with the ketones to make ketones, but this thing is already a ketone, so it's pretty much hydrating a ketone. So we have this, we have a ketone or an aldehyde, right? And then you just hydrate it with H2O with an acid or base, and pretty much you just add an OH. You just reduce the carbonyl to an OH. So this is where HR is, and then RR group, right? So that's it. With an acid, again, protonation first, right? And then second, attack. And then third, deprotonate. With a base, attack, and protonate. So that's the difference between there. Again, you kind of sensing a pattern. Acids are always protonating first because acids have protons, while base protonate last, right? So you kind of see the pattern there. So that's it. Just wanted to mention that hydration of aldehydes and ketones. And now for the good parts, acetal and hemiacetal. So hopefully I can fit this in one page. So acetal formation we have, and actually this one I have a note here, not ethers, right? Not ethers. Acetal formation we start off with again an aldehyde or ketone, right? Plus our O H, two equivalent, two equivalent, and again, I said acids goes back and forth, makes this acetyl go back and forth to an acetal or to back to the beginning, right? Aldehyde or ketone. So H plus, and then most of the time it will be TSOH is your acid. They'll go back and forth. And now this is what we get, right? We just make two OR groups, right? So I guess this is our right. That's our goal. The two OR groups, the acetyl formation. And again, it can go back, right? Just using an acid. Now, what if we use a diol? So same thing, right? But this time we use a diol. What happens? So same thing, right? H plus TSOH, and I don't think I have room. But this is where the protecting comes in. Or, and it's a diol because of the 2H, right? So that's that. That's the protecting. Protect, right? So you just need a diol, and you'll end up with protecting group, right? So there's that. And now for hemiacetal formation, everything's the same, but this one is just one equivalent, which makes sense because hemi means half, right? So one equivalent, and it'll just end up with we'll have OH over here, and then we'll have the OR over here, right? So yeah, we get half of the acetal. That's it. And then yeah, you can react it again with an ROH to get to the full acetal, right? So no big deal there. I'm dropping my pen a lot today. Okay, so no big deal there. So let's. I thought I could do this in one page, but now let's do hydrolysis of acetals, just to kind of to cement it, right? So acetal. I'm not gonna draw it this time, so we don't. So we can have more room. So acid H2O goes back to aldehyde or ketone, right? Which is what we were talking about. So don't forget that. You just need acid to get to an, and actually let me put an arrow here because it's the same, right? So there, right? And now we have the cyclic hemiacetal formation. So this one, the big thing about this one, like I said, the OR group is the ring, right? And then you'll end up with new stereocenter, which means two enantiomers, right? We haven't talked about stereoisomers in a while, but right, that makes sense. RNS, things like that. So with cyclic hemiacetal, all you need, again, same thing, same with just in hemiacetal, you need just another ROH to get the acetal, right? And the big thing with this is that only hemiacetal OH affected, right? So if there's other OHs there, those don't get reacted or those don't get oxidized, right? So make sure you're working with the hemiacetal OH alcohol. So with that all being said, that's all I'll have for you guys. I guess it didn't turn out to be that short because it's over an hour, but hopefully you guys learned something. Hopefully that helped. If anything, again, use those study questions. I encourage you guys to use those. Use all your resources, manipulate, pick every single detail, turn them upside down, ask the opposite question, and share. So, and again, if you don't understand anything, just come back to the video. And if you really don't understand anything, or if I really just confused you, go to your professors, right? Don't be afraid. Go to your SI, ask questions. I'm pretty sure SI has a similar type review guide type thing. So use them, right, while they're there. So thank you guys for watching, and I hope to see you guys next time.